Hi, good morning. I'm Richard Sharpe and I'm going to be talking about generating Wireshark dissectors, and this is pretty much a status report on the process of generating a Wireshark dissector. Just a small amount about me. I've contributed to Wireshark since about 1999 when it was called Ethereal. I've done a lot of work with wireless, well these days I do a lot of work with 802.11 protocols, wireless protocols. But over the years, I've done a bunch of other dissectors, including the first SMB dissector, the SMB1 dissector, FTP, TFTP, those sorts of things. But I've gotten more interested in generating dissectors. And so what I want to talk about is firstly, why would you want to generate a dissector? And I'll try to motivate that in a second, because where I currently work, we do in fact generate dissectors for something on the order of 12 to 15 XDR-based protocols that we are using. Then I'm going to look at a data structure approach. So I've developed a little language that is essentially a data structure language, and I'll talk about that a bit. And then we'll look at how it's being done. I'm using a tool called Antler and Java, because Antler generates Java code, and it was easy. It can generate other code, but it was easier to simply go with the Java code that it generates. But what's spat out the end, of course, is C code. And then I'll have a deeper look at the description language. When I look at Antler, I'll look at the grammar that describes the language, because you need to feed a grammar into Antler. And so then I'll have a deeper look at the description language and go through a bunch of examples based around a protocol called IEEE 1905 that I wrote a dissector for last year. For the Wi-Fi Alliance. A little bit about handling exceptions, because I've built some things into the language that describes the protocol that allows you to handle exceptions. Then I'll talk about what I currently have working, how far along I am with this. And it's, just as a preview, it's generating code, but I can't build the code at the moment, and it's only generating about probably 85% of a dissector at this stage. Problems that I have, problems with what I'm doing at the moment, i.e. issues, etc. And then where else this could go in the future, what it could be used for in the future. So, one of the problems, of course, is that Wireshark is complex. There's not a lot of dissector generators. There's not even a lot of developers, other developers. And there's a huge learning curve as well to writing dissectors. And so it kind of puts a lot of people off, people who are not familiar with it, etc. And so there is a need to be able to, in some cases at least, generate dissectors from some other language that can compactly describe the protocol that you're wanting to generate a dissector for. Another problem is here that protocols change, and we found this a lot at work with our XDR-based protocols. XDR is the protocol description language used for Sun RPC, so for NFS and things of that nature, and we use those. We also use I think we still use Swift, and we use protobufs, etc. But we had something on the order of 10 to 12 XDR-based protocols, and they were changing over the development cycle. So at the beginning of the development cycle, we would have one version of the protocol. Towards the end, new fields may have been added to that particular protocol, new requests or what have you. And then when we went to the next development cycle, we may have had a second version of the protocol. So in the early days, some people decided to write dissectors for one or two of them. They never got around to writing dissectors for all of them. And then the problem was either they didn't know how to do it correctly, and they didn't have the time to keep the dissector up to date as the protocol changed. So a couple of years ago, I wrote a dissector generator for XDR using this C. I took the, Sun RPC has a compiler called RPC Gen, and you feed it an XDR description of your protocol, and it spits out the client routines for marshalling the data structures into an on-the-wire structure, and it also spits out the server routines for unmarshalling and handing that data structure up to the server functions, etc. And so I modified RPC Gen to also spit out a Wireshark dissector. And so taking that approach was quite convenient because I didn't have to write a parser for my language. RPC Gen already had a parser for XDR. And so, more than 50% of the problem is in writing the parser and getting it correct. And so I just leveraged something that already existed, and it was also in common with what RPC Gen was already doing. And that turned out to be quite useful, and now every build we do at work builds a new version of Wireshark with those our dissectors built into it, so engineers and support and QA can actually look at the protocols on the wire if they want to and see what's going wrong. And I've done it before, as I mentioned, so I talked a little bit about this XDR one. The first SMB dissector I did way back in 2001 or 2002, I can't remember. That was done by, instead of writing thousands of lines of code, because that was a fairly big protocol, I wrote a small language and I wrote a Perl program to generate the dissector from that. Unfortunately, I never ever released that generator code, and that was probably a mistake because people might have found it a useful approach for other protocols for generating dissectors. So that's some of the reasons for generating dissectors. Now, are there any dissector generators already? Yes, there are, as you may have heard in one of the earlier talks. There's already an ASN1 dissector generator. So if your protocol is one of those protocols that uses ASN1 to describe it, like Kerberos, or LDAP, I think, is also uses ASN1, then you can pretty much generate a complete dissector. Although I think what they do is they generate it and then they run a script over it to do some fix-ups in the current build. IDL is another one, Interface Definition Language. That is Microsoft's RPC description for their RPC protocols. And there is a dissector generator for IDL that was contributed by somebody from the Samba team, because Samba implements the SMB protocol and implements a lot of the RPCs that Windows supports. And so they built an IDL compiler, and they extended it, I believe, to generate out the back of that as well, Wireshark dissectors. There's a private one that I just talked to you about, our private one at work for XDR. Now these two, IDL and XDR, take the view that we are going to implement a protocol on top of RPC, although actually possibly XDR is more in that vein, because NFS is a file serving protocol implemented on top of XDR, while the SMB protocol is a file serving protocol, a standalone file serving protocol, and then it has an RPC implementation layered on top of SMB. But those two are basically about RPC, remote procedure call functions. I've heard of at least one other private one that a company that's now defunct built. They built some, I think, Perl script as well that ran over the .h file that described their message, their requests, etc., and generated a dissector from that. And there may be one out there for Google's RPC. I'm not sure. It looks reasonably easy to do it, so there may be one out there. Now, what I focused on then, because I was doing a lot of work on wireless protocols and the sorts of protocols that come out of the Wi-Fi Alliance, where they tend to use an approach where they will get down to the bits and bytes in each request. They tend not to necessarily think of it as an RPC style protocol or a request. Well, they kind of tend to think of it as a request response type thing, but each of the requests and the responses are defined separately. And so I took the approach of, hey, each packet is essentially going to be a data structure. And then in that data structure, there'll be various types. There'll be bit fields, uint8 fields, byte fields, character fields, OUIs, because OUIs tend to be used quite a lot in the wireless protocols. There may be Ethernet fields, which is, you know, an Ethernet address consists of an OUI and a number within that OUI, uint16s, etc. And then there has to be a way to specify sub-data structures and use those. There has to be switch statements and arrays in here. And I'll talk about in a little while why there has to be, I'll give an example of why there have to be things like switch statements and arrays. And then you have to be able to specify some glue that allows you to construct this Wireshark dissector by specifying where in the set of tables that Wireshark uses that you want to insert your dissector, so how to get it into Wireshark and other dissector information. And so I started with this particular view. Now, before I get onto some more, here is an example of one of the structures, in fact, that the description language describes. So this specifies a structure called IEEE 1905 Steering BTM Report. I don't know what steering BTM really means, but it's some sort of a report. There is a BSSID. Now, this BSSID is some sort of data type. It happens to be a typedef that is not a basic part of the language that I generate. And then there's an Ethernet address in here, and you can see there is some of these strings, etc., a uint, a switch statement in here, and there are several cases in this switch statement, and this funny void thing here, which I'll talk about, and an exception statement. And then you terminate this set of braces here with a semicolon. I've gone with semicolons in lots of places to make it easier for the parser generator to generate. Now, I'll talk about all of those fields in detail and all of those concepts as we go along. So, as I mentioned before, the approach that I use is I use Antir4. There is this neat parser generator out there written by Terence Parr, a guy, P-A-R-R, I think it is, a guy who teaches at San Francisco University, called Antler. And Antler is written in Java. I believe an earlier version of Antler was used, in fact, with one of the next versions of the Java compiler. So it's kind of strange or interesting that Antler is being used to generate the parser for Java, and then it uses Java itself. It takes what is called an extended BNF file. If you know BNF from your college days, etc., Bacchus now, a format for a parser. It extends it with regular expressions, and I'll show some examples of that. And it generates a recursive descent parser. And the interesting thing here is that unlike, say, YAC, which generates an LALR parser, and an LALR is essentially doing bottom-up parsing, Antler does top-down parsing, and it can do some quite sophisticated error recovery when it runs into situations where the input does not quite match the grammar, and it can do things like inserting symbols or ignoring symbols until it resynchronizes, and it can generate reasonable errors. I'm told by various people that YAC, being an LALR parser generator, will give you some really weird error messages that are hard to understand. although I'm not using very much of the error recovery, etc., of Antler at this stage. And then, whoops, let's go back a second, and then I have written a bunch of Java. So Antler spits out a parser for me, and then that allows me to walk the parse tree and generate the dissector. And so the kind of the workflow that you have is you create a grammar file that describes the grammar of your language, and then you run it through Antler. That spits out a parser.java. Then you write a bunch of generator code that uses that parser, and that now dissector generator takes your protocol description that describes the protocol, you pass it through now this dissector generator, and it generates a C file which you then throw into the Wireshark directory, and you have to modify one file these days, cmakelist.txt, I think. Put your newly generated dissector into EPAN dissectors, and then you can build. And so it's a relatively simple process. So those are the steps that you take. And what I've found is Antler is actually quite nice because it's relatively easy to go around this loop here. When you say, oh, damn, I've made a mistake in the grammar, I need to modify the grammar to handle this new feature or what have you. Well, you go and modify your grammar file, push it through Antler, out comes this, then you try and build your Java application, and you may now get an error because you've changed something and the methods that have been spat out in here are slightly different, the data structures are slightly different, so then you go back and you modify potentially your protocol, you modify your protocol description probably because you changed the grammar file to allow for more sophisticated protocols, but you probably also have to modify this. But in the normal case, where what I've found is where you're not modifying the grammar file, typically my iteration is, okay, modify the generator code, then test it out, run it through the new generator here, the new dissector generator, look at the result, see if it looks correct. If it does look correct, then hand it to the Wireshark build and get Wireshark to build. If it doesn't build, then generally just have to go around this loop here, and I don't have to touch this until I need new features in the grammar. So I've talked about all of these pretty much. Also, the thing about Java is that it makes it fairly nice because what you are doing is extending an existing Java class that is spat out by Antler, and that your extensions then walk the parse tree, as I mentioned, and generate code. And there are some opportunities to do interesting things there as well with the sorts of things that you generate, and I'll talk about those later on. So what does our Antler grammar look like? Well, this is the beginning of my grammar file, and this is essentially a set of rules. This is the master rule here. It says that a protocol consists of, that plus sign is the regex extension. If you're familiar with regular expressions, then what this is saying is that a protocol consists of a proto-declaration or a proto-decal, one or more proto-decals. So the protocol must have one or more of these. And then a proto-decal consists of either a dissector table decal followed by a semicolon, or an endian decal, or a proto-details decal, or any one of these things, an enum, a struct, a typedef. I took the decision that a switch is not a standalone thing and can only occur in a structure. So you don't see the switch up here. And then as we go further down, an Endianness decal is either, it consists of the word Endian followed by an equal sign, followed by one of these two symbols, E under big or E under little. Now, in Antler, strings that are in all uppercase are lexical rules. So Antler distinguishes between lexical rules and between grammatical rules. rules. And lexical rules then tell it how to pull pieces apart. And so the actual strings are either big or little in here, and there'll be an endian statement in there somewhere saying big or little. And a rule is terminated by a semicolon, but notice I put explicit semicolons here in the language, and the rule itself has a terminal semicolon. And then there are some other things in here. So here I'm describing down here at the bottom here, I'm describing what a structure declaration looks like. And a structure declaration can be either an external declaration, and I put that in there in case you want to share structures with other dissectors, or it can be in a local declaration, or it can be an array declaration, or it can be a switch declaration, so that you can define all of these things. And there are some other interesting things in here. So an array declaration can consist of an ID followed by either an ID or a string, then followed by open square brackets, followed by another thing, a switch struct declaration. I'm not sure I have an example in here, but I'll show you why we do that in a short while. Or it can be an int. So you could say that an array just has an integer as the controlling element, specifying how long this array is going to be, followed by the closing square brackets and then the semicolon for the rule. And there are a few other things up here. This one in particular is kind of interesting because it allows me to split up a 16-bit or 8-bit or 32-bit field into a series of bits. Now I'll show you an example of these rather than perhaps just going through some of these rules in more detail. But however, a switch, so I did just put up here, a switch or structure element control field allows you to specify a field path, and a field path so I've borrowed some stuff from file systems here. What I'm saying is a field path can either have a .. on the front of it saying, I want to reference something above me, something above this element, or and then I allow slashes in there, and it can be a field followed by a slash followed by any number of fields, so that you can generate paths when you want to access these control elements. And there are some examples further on, and then there is just a bunch of operations. I can also have an expression in here saying, essentially it's a while this is not true, or while some field is greater than some other number, and so on. Then do various things, left shift, right shift, addition, subtraction, and ampersand for doing ANDing bits out of a field and those sorts of things, followed by an integer or an ID. Now these these brackets are grouping operators, and you may have seen, there are some other things in here. No, there's that star up there means 0 or more, and there may be, no, okay, I'm not sure I have. Now, these are some of the lexical rules. Antler gives you a fairly compact way to specify various lexical objects, like a string, for example, is something inside quotes. I've got a comment in there to myself to remember that I don't have a way to deal with embedded quotes as yet, so I'm probably going to have to extend the grammar or extend the lexical rules a little bit. A comment consists of a pound symbol followed by, now here's some interesting things, dot meaning any symbol, this is straight regex stuff, star meaning any number of them, and in fact that comma there is probably redundant. Comma means it can be absent, it's optional, but since dot star is already optional because star means 0 or more, the comma is probably redundant. Followed by any one of these square brackets now means I can choose these things. So carriage return /n and /r, if those appear in there, that's a comment, and this is a rule as well saying throw it away, I don't want it, skip it. An ID consists of lowercase a through z, uppercase a through z. So the first letter has to be a letter from the alphabet, either lower or uppercase. Then A through Z, lower and upper, and 0 through 9, and underscore. I allow underscore in there. 0 or more of these things. So an identifier can consist of one of those things. White space is a space, tab, new line, carriage return. One or more of them, I throw them away, skip them, we're not interested in them. An integer consists of either a hexadecimal number, 0 through 9, A through F, etc., or 0 through 9, one or more of those. So I can deal with both decimal and hexadecimal numbers. Maybe we could add octal, but most people don't care too much about octal these days, although some older protocols do. So that's that's a little bit about the grammar that I use to generate the parser. Now the next step is to have a look at the actual language and give you some examples of the language that this describes. And so some things that it describes are Endianness. It tells the generator what the top level data structure is in Wireshark, because you always have a top level data structure that you're going to start with. And so that's the main function that Wireshark is going to call in your dissector. You can specify field types and field names. There are Typedefs, Enums, switch statements and arrays, and structures. So these are all of the various things. And so the first one is an endian statement. If you don't specify an endian statement, it defaults to big endian. If you were in Graham's talk yesterday as well, I currently do not allow you to switch endian type for a particular protocol. I guess I could add that at some point, but you specify it at the beginning. If you don't specify it, then it's big endian. If you do specify it, it's little endian. Actually, I don't think it matters where you specify it, because the parser generator gets a hold of this information and can get a hold of it anywhere. So then these are some boilerplate details. You specify, hey, these are the three fields that essentially you need in a Wireshark dissector dissector. When you register the protocol, you specify these three fields. Then this is the top level data structure here, this thing here, and so there must be a structure definition that matches this and describes this. And then this specifies the table that you insert into. I think there is a mistake here, because I noticed, and I'm going to have to change that, this should probably be a string, because I noticed that there are some dissector tables that take strings as their inputs in order to figure out which dissector to call. So I'll probably have to change that in the longer term. Then you have a whole series of field types, and so bit, byte, int8, uint8, etc., up to uint64, Ethernet, OUI, and I think there are some aliases for these. And then you have this concept of subdivisions. Subdivisions, and I'll talk about this again in a little bit, but subdivisions allow you to subdivide a byte field or a 16-bit field into a series of bit fields. And the way you do it is in the language that I developed, you specify the base type, whether it's a uint8 or a uint16 or whatever. Then you specify a series of either bit ranges or bits here, and give those a type, although some of these types, they don't actually match, because that's 5 bits there and that's 2 bits there, and I've called them uint8 for convenience. And then you specify a label, and a label can have quotes around it, because you might want to put spaces in there, and that label specifies how it's going to be displayed. So in this is a cutout of a part of a Wireshark display. Then this extiv field would come from this label here, and this 5-bit here says, hey, I want you to use this bit to represent this particular value. And because I'm using possibly an enum here, this could be the value from the enum. So you can get down to defining bit fields like that. But this is another example. Here we have a whole bunch of field names that are written as strings with their types before them. Two of those, uint8, are built-in types. BSSID is probably a typedef, and I've just repeated the same picture here as another example of what that might look like. And again, this is another case where I'm doing various bit fields here. Now, this is a single bit, and I think we'll see something associated with it. These two are Booleans, and this is just treated as a 5-bit uint field called reserved. And each of those then have strings there. You don't have to use strings, but if you don't, then you have to put underscores between the components, and it will print them out exactly as they are. So using strings makes things prettier when it's displayed on Wireshark. This shows typedefs and enums. Typedefs are just a convenience. We could always specify as an array, because this BSSID is just an array of 6 bytes and will be displayed as a byte string in Wireshark. So this gives you some idea of the meaning of an array. So this is a 6-byte string. This, however, is an enum, and this is the channel preferences, the preference values, and I've specified that as a uint4, although I'm not sure that I'm actually checking that carefully at the moment. And then here you specify the numbers that are associated with strings that would appear in the middle pane, in the detail pane, for each of those values. So this is for translating to each of those values, but you also have the opportunity to specify symbols associated with these. And the reason for specifying symbols is that you can use them in switch statements, although you can also use numbers in switch statements, but it makes things a little bit more convenient. You also have a default value in here where you can say what the default should be. Either it's reserved or unknown or whatever you want to choose as the default. What I don't have at the moment is something similar to Wireshark's range strings, where you can say a range of values produces this number or what have you. And okay, so moving on, this is what in fact, there are 2 examples of switch statements in here. Now, and I'll motivate in a second why you want switch statements with a diagram. But essentially, this one is saying, look inside this field in the current structure and look for this subfield. So this actually has to be a field in the current structure, and that'll translate into a data type, some sort of structure in fact, and then look in this field for the value, and then use that value to determine what you're going to do. This value void here is a special one that means actually do nothing. There's no need to deal with this, and there are some cases where you need void, and we'll see void a little later in a realistic case. Otherwise, if it's a request is steering mandate type, whatever that name translates to, then the data structure that should appear here is a steering op window. So that then allows it to, and these actually translate roughly into switch statements in the C code. Another switch statement here, this one says, go back up 1 level to the structure above us. So it's here relating to us, our structure being embedded in another structure. So go back up 1 level, go down in the TLV header and get the TLV length, and then subtract 13 from that. And then if the value is 6, then we've got a target BSSID in here. If the value is 0, do nothing. And otherwise generate an exception saying that we've got a malformed steering BTM report, blah, blah, blah. And so the switch here becomes kind of an if statement as well. It's kind of an if with a little bit extra in it that you can do. Now, the reason we need switch statements, of course, is that there's one top-level structure that we're going to dissect, that is associated with the protocol. And that top-level structure will have a header of some sort, typically with a type in it, but the body in each of those will be potentially of different sizes. They may be of the same size, but they may have different structures. So these switch statements allow us to handle this particular type of thing. And then there are arrays. The little language that I've designed also allows us to use arrays, and so this is an example. An IEEE 1905 channel preference has a radio ID in there. A radio ID, this is probably another typedef, which is 6 bytes or something of that nature, because it looks a little bit like a BSSID, and so that the label that would appear inside the detail pane is radio unique identifier. Then it's followed by a uint8, which is the number of operating classes in this structure, and then it's followed by a structure, channel preference details. So channel preference details would be defined somewhere else in this file, and the label that's applied to that is operating class list, but it's an array, and the length of that array is controlled by this operating class's value earlier in the structure. And so what it looks like, I think you can just see the dividing lines between these things. Here's your packet. Somewhere above there's a header in here. Then we come across this, somewhere along here, we come across this operating classes, and that controls how many of these following things we're going to dissect. So we generate code to dissect each of those based on the number that we pulled out of this particular field. And so this value here can be either just a straight number like 6 or 10 or what have you, or it can be a value in the current structure, or it can be a value embedded in a substructure here, or we can go back up the hierarchy of structures and use a value that's further above us, or that we don't have direct access to. And I've put this up because this shows this is the top level structure for IEEE 1905, and it consists of a bunch of these things. There's an enum here, so the first field is a message version with an enum. Then there's a reserved field. Then there's a message type field in here, a message ID, fragment ID, uint16, u8. Then there is one of these subdivided fields, a uint8 field that has a couple of useful bits in it, and the rest of the bits are reserved. Then finally, they use TLVs, type length value fields. There's quite a lot of IEEE Wi-Fi protocols that use TLVs, where the structure has a type, a 16-bit or an 8-bit type, a length, an 8 or a 16-bit length, followed by a value. And the length specifies how long the value is. And so you need to deal with these things. And their protocol says that there is going to be a series of TLVs in this CMDU, a command unit. There will be a series of TLVs. And what they further specified was that there should always be an EOM, an end of message TLV, in one of these CMDUs. And an end of message TLV is a TLV with a type of 0 and a length of 0, so it has no body. And so what I did in the language is I said, well, hey, we know when this array of protocol TLVs is done when we see a type in here of value 0. So this is kind of a while statement which says while the protocol, but it's also self-referential, while the value in this structure, in the TLV header in that structure, in the TLV type is not 0, keep on dissecting these protocol TLVs. When you hit one that is 0, now you expect to see an end of message TLV as well. And the reason for putting that here is if you see anything beyond the end of message TLV, and when they were doing testing, they gave me a bunch of captures where there was rubbish beyond the end of message TLV, then that's an error. And so this gives you a way to detect those sorts of errors. Unfortunately, this makes the language somewhat more complex, and I haven't yet managed to generate code to handle this particular thing, this particular structure. And okay, so now here is what a protocol TLV looks like. So it's got a TLV header in here, which is of type TLV header, and I haven't shown you what one of those are, but it's just basically a type field and a length field in there. And then I have a switch statement in here which refers to that TLV header and is taking the type field out of that TLV header. This much is working and generates reasonable code. If it's an end of message type, then void. We have no structure following that. So all we get is the TLV header. But if it's one of these other things, then there's a structure associated with that. And if it's a default, then we can print out an exception. And the intent here is that we can use standard printf type strings in here to say, hey, it's an unknown TLV type, and this is the value of that unknown TLV type, so that you can interpolate various things into there. And so now, how do we deal with exceptions? This is a little bit more about exceptions here. So what I'm planning to do, because this also is only partially handled, is you can have an example like the one I showed you before, where you can specify that it's an exception, or you can use debug, because there are several loosely types of exceptions you might want to refer to. You might want to put a debug entry in there. You might want to put a warning entry in there. So there are a variety of different ways to do these exceptions and various strings. They look like function calls because that's the way I think of them. But the language handles it reasonably well. So, what are some of the problems?
I'm sorry, I've got a quick question.
Yes.
I'm seeing that for value 11, it's vendor specific. How would you handle that when you don't know? Or I'm sorry, for the type 11 is vendor specific. When you don't know what the value would then be, how would you account for that?
Oh, which you mean you're actually looking at 1905 at the moment? Yes.
Just for just on the Wikipedia page, it says that type 11 is vendor specific. Yep,
sure. So the vendor specific one, they have defined vendor specific to be a whole heap of unrecognized bytes, basically opaque bytes. But that's where earlier on I talked about let's go way back. One of the things in the language that I've put in there is this one here, external ELT declaration. That's how I plan to handle things like vendor specific, because they do actually say, we don't define what this field looks like, but some other specification defines it. So the intent then is that I can treat the length of that value, treat the blob that's there as a blob, and call an external dissector through a dissector table, for example. Now, I haven't done anything about that so far, but that's where I'm intending to go with that.
You're really just hoping that the vendors actually disclose what that field is?
Yes. If there is none, then it'll have to be dissected as just a straight blob of data. And by the way, you're welcome to give me feedback and comments and suggestions about where this could go, etc. Now, so, right. So now there are some problems, of course. This is really the way it's going at the moment, only useful for new protocols, or if you want to go and rewrite in total an existing protocol. So let's say somebody manually generated the dissector for Telnet or FTP or something like that, and you wanted to get away from that hand-built code, then you would generate a completely new, you would describe the FTP language using my language description, and I haven't thought about whether or not it can deal with that, because there are some other interesting things that are going on in there. But then you would just use that to generate the dissectors from scratch. And it's focused pretty much on Wireshark dissectors. And I haven't gotten around to doing things like handling preferences, say, because Wireshark gives you the ability to do preferences. It gives you the ability to keep state information. I haven't gotten around to thinking about how to deal with state information, which would be very useful for Wireshark. those are a couple of the things that I will need to do additional work on. But so it's really for new protocols, and to a certain extent it's designed to allow people like the Wi-Fi Alliance to generate dissectors for these new protocols that they are coming up with and testing as part of the whole Wi-Fi infrastructure, the whole Wi-Fi community, etc. And so what's the status? It's about 85% done. It's written in Java, as I mentioned. It just turned out to be easier because the Antler by default spits out Java. It can spit out C++ and Python and JavaScript. So there are alternatives there, but I've decided to do everything in Java for the moment, although it spits out C. I haven't handled self-relative array indexes yet, and I haven't handled things like the HF declarations, the ETT declarations, and the boilerplate and some small things. These are going to be relatively easy to do because it's simply a matter of running through a list that's already been constructed in some fashion and spitting out some very, very simple text. But this self-relative array indexes is a little bit harder and will require a little bit more coding. But so far I've found it relatively easy. If I have to modify the language description in Java, the Antler language description, run it through Antler again, then fix up the Java because new classes were defined or what have you, and go through here. And I have a debugging system in there where you can specify you want debugging and it'll spit out a lot of information when it's generating code so you can see what's gone wrong. Otherwise it won't spit that stuff out. In fact, on a cruise that I recently took, initially I had a whole lot of system.out.println statements in there with debugging, and I realized, hey, this is a bit of a pain. Because I need to switch it off, so I wrote a quick class to handle debugging and allow me to switch it on and switch it off. So probably in another month or so, maybe 2 months, I will be at the point where this is generating for my example, which is IEEE 1905. I want to be able to generate the whole of IEEE 1905, that dissector, and today that's about 5,800 lines of code. And I want to be able to generate all of that with equivalent, in fact, better functionality than we have at the moment. And so in another month or two, I think I will be there. Now, there are some things that we could do further with this sort of approach. One of the things we could do is to generate packet generators. So once you have the description of a protocol, you can then generate code to do fuzzing, for example. Yes, I mentioned fuzzing. So you can generate a packet generator that will generate packets with random or non-random data in there for testing your dissectors, for testing implementations, for doing fuzz testing, etc. One of the other things you could do is for generating libraries to actually create or pass these sorts of packets so that you can be a little bit more lightweight than, say, using T-Sharp or Wireshark. If you're trying to, a lot of people put T-Sharp into their tool set and they run a PCAP through T-Sharp, and it'll spit out a bunch of information, and then they grep it or whatever, or they insert that information into a database, those sorts of things. So this could be a more lightweight, it could be generating libraries to be a more lightweight version, but it'll need different code generation backends. And from that perspective, so today what happens, of course, is there's a parser that's generated by Antler, there's the tree walker, which is handwritten by me, and the dissector generator. And the reality is that these two things are actually the same piece of code, but I plan to split it out because you could envision having other back ends here, like a protocol fuzzing generator or a protocol library generator as different back ends for this thing. And one more thought that I had is that, you know, in reality, a protocol is typically just a list of key value pairs. You can think of it as a list of key value pairs. Even a PCAP file itself is just a list of key value pairs. Of course, some of those values may have arrays or other key value pairs in them, but they're essentially just a key value pair. So you could generate a program to convert a PCAP file to JSON or whatever you want in here for your testing and those sorts of things, for unit tests and other tests. Okay, that's it for today. I've gone a little bit over time, I think. But any questions or feedback?
Will be available for testing soon?
Yeah, give me a month or two, and I'll put it up on GitLab probably. And I don't have a make file yet, but that's easy to create. And then yeah, I'll put it up on there, and we can see how it evolves.
So the Antler.
Yes.
Can you go back to that workflow?
Yes. This one.
Yeah. So basically, we are using this to generate a C file, right?
Yes. So out the bottom, we spit out a C file here.
So,
now it doesn't have to be C; it could be another language, of course.
But then Wireshark does not understand it.
Right. So Wireshark doesn't the Wireshark dissectors have to be in C. But if this was being targeted for something else, you could envision that what it would spit out, it might spit out C or it might spit out Python, but it could spit out a program that knows how to open a PCAP file and how to read each of the entries in the PCAP file, and then for each of those entries, call the appropriate dissector. So, and I mentioned, there's no way perhaps to draw it here, but you know, a PCAP file is nothing more than really a series of key value pairs, and so you could build up a series of arrays. So the first level would be a description of the PCAP file plus the various protocols that are in there, which is typically Ethernet types. And with a relatively small amount of description, you could get yourself to the point where in Python or in another language, C++, or even in Java, it could be passing through a PCAP file and pulling out the relevant things that you want.
So I just feel there's just so much going on over there to generate a C file.
Yes.
Like we have an Antler, and then it goes out a Java file, and then we are putting it to this dissector to eventually come into a C file.
Yes.
Is there, do you feel like there's some way of us to like skip any of these intermediate steps? Or is it because like Antler can only dissolve into a Java?
Oh, so I see. So there is, Antler actually can generate C directly. I think somebody has done a C generation directly. I guess there are two ways that we could go here. However, one way is, so this has been focused on generating C, as you say, which you have to compile. You could put an interpreter in here, and you could have Antler generate, it would be here, generate an interpreter like Lua code, for example, instead of generating all the way to C. And that Lua code could then just be put into a directory in Wireshark and go from there. That would reduce the number of steps. It would not be, say, as efficient when in runtime, but for people who are, so, there tends to be two classes of people who are using Wireshark. There are those people who are using Wireshark just to look at the packets that are being spat out by their application to check to see what's going wrong in this particular area. And in those cases, they probably don't care too much about how efficient it is, because if it takes 20 seconds to load or 30 seconds to load, who cares? There's probably only 30 or 100 or 200 packets or what have you in there. Then there are other people who deal with gigabytes of data, and there are some people in between, of course, but there are people who deal with really, really large data sets. So that's actually an idea that I need to think about, is whether or not I could say generate Lua straight out of in here as this step, for example, and combine some of this. And then if I'm generating Lua, you don't have to deal with the Wireshark build system as well, for those people who don't want to have to deal with the Wireshark build system. So that's a good suggestion.
Yeah, because I mean, if I have to, if my endpoint is to generate this direct dissected seed, I guess you're right. Why would I use that?
Well, no, yes, but the thing is, some of the earlier things I mentioned, usually during a development cycle, your protocol actually changes, and so you don't want to be on the hook for having to keep it up to date. By generating the C, there is some value. It's automatically, once you change the description of your language, and the example I gave was, say, the XDR-based dissectors. However, of course, there would only be value if you were using this protocol description in other parts of your build as well. If you're only using the protocol description for Wireshark, there's possibly less value, although it's more likely, it's easier probably to keep this up to date than to keep this up to date. So there is some value there. Anybody else? No? Okay, well, I hope this has been useful, and I'll keep working on it. And yeah. Thank you.